Dear AICT 2021 conference participants, let me present my paper on consistent MDA for workflow development. My name is Timur Umarov. During this presentation, I will give a little background information and be talking about current state of the art of business processes and the problem of semantic gap between high-level specifications and design decisions. I will be describing our approach on using patronets and combining it with the B method. This will be followed by the discussion on preserving correctness of artifacts written in B. I will demonstrate a little example at the end. Business process management, or BPM, is an increasingly important issue for the enterprise. Software support for BPM has encountered several challenges related to scalability, performance, and maintenance of workflows through the emergence of workflow management middleware. However, the following observations have to be made regarding the state of the art. The problem of improving and optimizing workflow regularly occurs because of constant change to the enterprise. For example, the growth of a company, changes to the market, revelation of tasks to minimize cost. All these factors often require radical re-engineering or redesigning of business processes, along with continuous improvement of individual activities for achieving significant improvements of performance-critical parameters, such as quality, cost, and speed. Re-engineering of a complex workflow implementation is dangerous due to multiple dependencies between tasks. Formal methods are often touted as a solution to the problem of complex systems development. There are a large number of case studies that show business process modeling and analysis with patronets that can greatly assist in eliminating liveness errors from an implementation. Similarly, the B method has had success in developing guaranteed, correct modular code from logical specifications. Patronets are used to model the possible flow of information in a given business process, but they do not specify the nature of the information. We also don't know how this information is to be manipulated. As we know, the data in patronets is represented as tokens, and they are not sufficiently rich semantically for business process analysts and for developers. However, formal methods alone are not a practical solution to the problem of industrial workflow development. This is because there is an inherent abstraction gap between specification and implementation roles. Business process analysis is a long-established domain, separate from recent movements in software business process management. Workflow design is always done by a business process expert who is likely to have no formal methods background and little knowledge of BPM software. The initial workflow design document that is given to developers is written without platform-specific knowledge. This is a different situation from ordinary software development, where requirements analysis and design are usually undertaken by a member of the team who has a background in programming. If we decide to employ formal methods, their use entails a bridge between the business process analyst's document and the platform-specific implementation. In this paper, we explore the use of model-driven architecture as a means of bridging the abstraction gap between business process analysis, formal methods development, and implementation in a typical enterprise middleware. The overall MDA approach is shown on this slide. We use patronets to model and analyze workflows. We are primarily interested in modeling and analyzing workflows and checking the correctness of them by means of applying mathematical techniques such as B method, which is a formal approach which utilizes abstract machine notation and is intended to be used for development of computer software systems, as well as programming language code from specification. B method is particularly useful for checking the specifications of a system for consistency and correctness. The former is concerned with the preservation of invariance, and the latter verifies data and algorithmic refinements during the course of code generation. Optimization of business processes should be mostly performed by business analysts. Unfortunately, long and verbose code, which are extensively used in business process definitions, are not as plain as they should be for non-technical analysts. This causes the involvement of experienced technical staff for reflecting the changes proposed in the business process specifications. Despite additional costs, there may also be possible errors conceived during communication between people, which consequently make the whole optimization process time-consuming and counterproductive. Ultimately, this may have its negative influence on the overall company's performance. For this purpose, the use of more intuitive and simpler formal modeling tools for defining and modifying existing business processes can eliminate the barrier between business analysts, managers, and IT experts. We consider business process from the perspective of computing. We first describe business processes using formal techniques, such as patronets. This slide shows a formal definition of a patronet. For the purpose of developing formal specifications for our PIM and transformation of patronets to PSM, we have given a detailed meta-level descriptions in our earlier works. On this slide, we illustrate a meta model of patronets and an instantiation of the meta model as per object-oriented paradigm. We have provided a definition of a B machine in our earlier papers. So for the purposes of this presentation, we depict a formal definition of patronets and B combined. So this slide and the following 3 slides, they show the formal definition of B combined, mapping of places and transitions to operations in the B method. After having defined the formal specification of patronet guided B machines, mapping from patronets to PN guided B can now be described in an informal way. We are mainly interested in performing the first stage of transformation, which is mapping workflow design to system model. This kind of transformation provides for mapping each element of a particular net of a workflow design written in patronets to places and transitions of PN guided B machine. Routing paths of patronets are transformed such that they preserve the rules defined for sequential and or routing with respect to the combined PN and B. PN plus B definition also provides for uses and sees cases. In our case, we're particularly interested in the sees constructs. Mapping of these constructs are performed by virtue of preserving the appropriate rules defined in PN plus B. The transformation should ultimately produce a consistent model such that this model satisfies PN plus B consistency rules. An abstract machine that we obtain from the PN and PN plus B transformation as a system model is an abstract specification of the PN plus B machine. This abstract model is not suitable for PIM to PSM transformation and by far for direct execution on the computer. Therefore, we have to perform several stages of refinement within the system model. The refined model will then be more concrete and detailed enough for further PN plus B to code transformation. Each stage of refinement is related to each other by means of linking invariants. Besides linking invariants and refinement machine will also have exactly the same interface as the machine it refines. This means that the refinement machine will have the same operations as the abstract one, and each operation will have the same signature, same input and same output parameters. A trivial example of making electronic payment on an e-commerce website using a credit card demonstrated here on this slide reveals this form of abstraction. According to this net, we have 5 places and 4 transitions. We're using abstraction and implying that in this place there are some computational procedures to be executed before it makes a decision, which transition should further fire. If payment data are validated, then transaction is accepted or rejected otherwise. This means that the place processing implies a non-deterministic choice, which is resolved by means of some logical computations performed inside of this place. We're assuming that the system only checks whether first the customer is in the database, second, whether his/her name corresponds to the credit card name provided, and third, whether the purchase price exceeds or doesn't exceed the credit line. Upon performing the check, if data provided is correct and purchase price does not exceed the credit line, then the next transition fires. The abstract model of the process transaction can be represented by the machine illustrated on this slide. This model represents a simple system of purchasing a product in e-store by a customer. In this machine, we first declare sets customer, e-store, and report. The main variable product represents a bidirectional relation between the customer and e-store sets. The main operation declared in this machine is processing, definition of which is deferred. The return value of the operation indicates whether purchase was successful. Our transaction model should have access to certain variables that are necessary for execution. For this reason, we have to have a repository of simple variables, name, card number, and total that we will use for our P n plus B machine. The transaction machine will be able to access this repository. The library machine illustrated here will represent the pool of all necessary variables. We also need to define a set of clients and their respective information, which the main transaction machine will have access to. This database machine is given here. According to this machine, the collection of the set's name, card number, and credit limit represents information on customers, their names and their card numbers and credit limits. In this database, the sets of information are related by functions owns and is limited to. The fact that owns and is limited to our functions effectively means that each person can be associated with no more than one credit card, and that each credit card can be associated with no more than one credit limit. The proof obligation for the abstract machine is shown on this slide. We can now develop a refined version of the abstract transaction machine, which is shown on this slide. A refinement of this machine introduces a new set of variables in progress and is verified. Both sets are initialized to be empty. The linking invariant defines these variables along with the relationship between abstract and refined states. Refinement also provides the definition of operation processing. The proof obligation of the refinement machine is shown on this slide. It's a bit longer because it covers the refined machine. So to recap, we have addressed the problem of abstraction gap that exists between requirements and design by using an MDA approach. Formal tools and methods like Petrinet's and B method and their combination were used to formalize the specifications, and B machine transaction was refined to a more concrete transaction R machine, thereby providing the lacking semantic description to the Petrinet. Thank you very much. Thank you very much for your attention.